everyone, this is Bao Xiang. I'm going to talk about global seasonal forecast via probabilistic deep learning. So the importance of seasonal forecast, which is forecast with lead time of 3 months up to 1 year, is needless to stress. It's really important for agriculture, energy, security, and many other departments. So we have several barriers that prevent us from really realizing the potential of seasonal forecast. But before that, let's talk about how can we make good seasonal forecast. A good seasonal forecast relies on the existence of key prediction sources, such as those variables that have low frequency, including the sea surface temperature and like sea ice and stratosphere. So then these key prediction sources may exert influences on the predictions that we care about, such as the local precipitation or temperature variation. But what prevents us from really fully realizing the potential of seasonal prediction? Let's see how we make predictions using a process-based model. Imagine we have a model here, and we have observations of the current status of the climate. So we try to use the observations to constrain the model state to make it in accordance with the current observations. And we integrate the model forward in time. And we know that it's a chaotic system, so beyond 2 weeks we can no longer make deterministic forecast, and there will be a forecast spread here. So there are 3 barriers. The first is that we cannot perfectly initialize the model so that the model state is in perfect accordance with the reality. And we have something called state shock because we are coupling individually initialized models. And they may have imbalance regarding their mass and energy interactions. And the other thing is that the model is not perfect because there are some small scale uncertainties in their parameterization schemes and how these schemes get along with the model's dynamics. So we have the model population errors, and this trajectory might be shifted a little bit up or down. And finally, we know that it's a very large dimensional system. Like we have 10 to the 7th power of geogrids for the atmosphere and 10 to the 8th power of grids for the ocean. So how can we guarantee that with limited ensemble member we can sufficiently sample this forecast spread? We don't know how many forecast spread we should have to make this prediction to have the probabilistic forecast meaningful. So these are the 3 barriers: per initialization, per model, and insufficient sampling of the forecast spread. So beside this dynamical forecasting paradigm, we have something called empirical seasonal forecast. And it has really a longer history than dynamical forecast. Here, I clarify them, I categorize them into 3 different periods. First is the first rise, which dates back to the 1920s to 1976, around that time. We have worker find the worker circulation, which is the circulation pattern of the tropical ocean. And we have Birknes who explain the southern oscillation and impact. And we have Claude Hasselmann who developed the principal component analysis that try to disentangle the signal and noise in climate models and in climate observations, trying to identify some human-introduced climate change signal or some like decadal or longer period climate signals. So I call this the first rise of empirical seasonal forecast. We notify that there are some low frequency signals, and we can utilize these low frequency signals to help us predict what will happen in the prediction that we care about. But gradually, with the development of numerical weather prediction models, and for benefit is the numerical computer techniques. So we gradually are able to resolve the climate dynamics or the atmospheric dynamics using these discretized numerical solvers. The pioneers are Giucciani and Norman and Suki Monabi. So this different from the pure empirical dynamical signal forecast, we have a consistent improvement of dynamical signal forecast systems. So this marks a fall of empirical signal forecast because as the dynamical forecast consistently improves, the importance for the empirical signal forecast to guide the improvement of dynamical signal forecast or our process understanding gradually declines. But since the year 2012 or 2018, roughly around that time, we do see a renaissance of empirical signal forecast. That is, although we don't have enough empirical observations to guide the development of sophisticated empirical signal forecast systems, but we can first train an empirical forecasting model, train a statistical model using the like well-controlled simulations. Later, we can just transfer these trained models to reality by either fine-tuning the model or just examining how this model works in reality. So here are two very important papers. One is using the singular value decomposition. I think it's like that to find the status in climate simulations that is similar to observations, and then use the later status as the prediction and try to apply it in reality. And the other paper, which is pretty popular right now, is deep learning for multi-year answer forecast. And they try to take predictor pairs from climate simulations and build a deep neural network, a convolutional neural network to predict the simulated relationship, and then fine-tune this relationship in reality. That called this re-rise of empirical signal forecast. So how could this re-rise of empirical signal forecast contribute to solid progress in our understanding of signal forecast? There are some implications here. First, GCMs, global climate models or general circulation models, they obtain their signal forecast skill from K-prediction sources. And machine learning can summarize how these K-prediction sources modulate seasonal variability in those model simulations. Often this is called analog forecast or phenomenological forecast. But there are some deficiencies in this methodology. So existing works, they usually focus on limited regions or specific climate phenomena, and there are no rigorous representations of uncertainty. Here we have several different uncertainties. The first one is about the initialization or the neglectable and avoidable growth of initialization errors. So we usually call this aleatoric uncertainty because we cannot remove them given the limited resolution of our model. So those uncertainties must be sampled or estimated. And there is something called epistemic uncertainty, which represents that the model is not a perfect model as we apply it to represent reality. So this epistemic uncertainty must be minimized. And if we just put these uncertainties together, like what they did here, we cannot really disentangle these two uncertainties or make good use of the data. So if we cannot make good use of this data, we cannot have a clear suggestion about how to conquer these three forecasting barriers. And our objective here is to develop a machine learning algorithm that can help us make global signal forecast with rigorous treatment of two different uncertainties in signal forecast and offer a clear suggestion to conquer the forecasting barriers. So how could we formulate the global signal forecast problem as a machine learning problem? We have all the climate simulations from two generations of cowpot model in the comparison project. So the X is the prediction source, which we use the upper ocean heat content in the present time, and Y is the predictant, which is what we care about. It's the next season's global precipitation or temperature map. And M indexes the model, the climate model, that generates the prediction source and predictant. What we want to do is to develop a generative model of probability of the predictant given the prediction source and which model that generated this data. So what we developed here is a customized conditional variational autoencoder model. There are some crucial techniques here. First, we use stochastic gradient variational base to estimate this high-dimensional distribution. For example, here, y is the global distribution of precipitation or temperature. If it's a 2 times 2 degree global map, we have 19 times 180 degrees here. And also, the m here is a categorical variable, which means which model it is. So we use the so-called entity embedding technique for latent vector representation of the GCM of the data generating climate model. And within this structure, we use convolutional neural network and transposed convolution or deconvolutional neural network to do the feature learning to serve as the building block of this model. We know that it's not perfect because it's spherical data and we are using a plenary convolutional neural network. We should use graph neural network, like spherical convolutional neural network. But this is just a work that set up some base for future explorations. For now, let's just say we use convolution and deconvolutional neural network for feature learning. And let me give some words about stochastic gradient variational base, or so-called variational autoencoder. What this method represents is that we have a high-dimensional distribution that we don't know, but we only have limited samples here. How can we estimate the distribution of this high-dimensional distribution? Or how can we efficiently draw samples from this distribution? What we did here is we built a functional mapping between this well-known Proud distribution, which might be a standard Gaussian distribution, and this unknown distribution. And we want each point here to be corresponding to a posterior distribution here, like PZ giving X. And we want all the points here to take up all the spaces in the target distribution. And this can be written in these two requirements. That is optimal latent for explaining the data here, and fully exploiting the Proud. That is, all the points here should take up all these spaces here. And this can be written in these two equations, which together are called as the evidence lower bound of the conditional log likelihood. And actually, we are trying to maximize this elbow equation in our implementation. And we use like 138,000 of years of climate simulation from 12 GCMs and the different forcing scenarios to train our model. It's a pretty it's kind of a pretty big data set, which together takes up around 2 terabytes of disk space. So here are some of the results, and we can train a model. But how can we evaluate them? Let's first see. We try to use this model to simulate how X regulates the distribution of Y in a single model. Here we use the CAN-ESM Canadian System model as an example. And here we have our methodology, we call it conditional generative forecasting methodology. How it applies for the CAN-ESM simulation, the model world for precipitation estimation. And this is the anomaly correlation coefficient, and how this relationship applies to real world, and how this dynamical model applies to real world if we use it directly to make simulations, to make predictions. And the very first thing we see here is that they have very similar patterns, meaning that these predictions are based on a same model, while this simulation here is kind of like resembles reality. But if we make comparisons of different pairs, we can find something interesting. For example, here, if we apply this deep learning model for model world and for real world, we see something interesting happening here. That is, the model believes that the maritime continent is pretty predictable with a correlation coefficient of around 0.7. But if we apply this relationship for real world forecast, the correlation coefficient is below 0.2, which means that the model extracts shows an overconfident relationship in how the ocean content regulates the precipitation for maritime continent. However, this relationship fails to apply in reality. This is an overconfident failure of the model. And the other thing is that we see that our model sometimes it surpasses if we surpass the performance if we directly apply this climate model for real world forecast. That's maybe because that we are using the conditional generative forecasting model, which can really generate a lot of ensemble members and making good use of this forecasting model. We'll come back to this issue in the later slide. And these similar results can be found in this in the forecast of temperature. So this is for temperature forecast. This is an ensemble forecasting thing. That is, we have this here. We are just using this model, but here we can also use a lot of different models and try to make predictions. And we see that we develop two different strategies. The first is blindly have each model, each GCM climate model, offer same amount of ensemble members. But also we can search the model embedding space to find something between all these model embedding vectors that provide the best forecasting performance. And we can also explore how this optimal model embedding resides in this model embedding space. And finally, we have we have 4 different dynamic models that they provide the ensemble dynamic forecast. So these are the results for temperature. A similar thing, but more obvious, that is in the model world, a seasonal forecast is really an easy task. That the July ocean heat content really give a strong regularization on the next season's temperature distribution, while this relationship failed to apply as well in the real world as compared to the model world. And the other thing is that our dynamical models, we know that dynamical models, when they make seasonal forecasts, they have to provide a good sampling of the possible forecast spread. But surely we cannot afford a lot of forecast ensemble members. Here we are just saying that in all these 140,000 years of simulations, we try to see that given a same ocean heat content status, we can generate as many ensemble members as possible with very little computational cost. And here we're trying to see, using this conditional generative forecasting methodology, as we keep increasing the forecast ensemble member, how the forecast still improves. And here the red one is the dynamical forecast. We know that if we increase the forecasting member, we have an overall higher correlation coefficient. But we don't have enough members. We can expect that we have a higher scale if we keep increasing the ensemble member, but we don't have these resources. And here, using this conditional generative forecasting methodology, we can create a lot of members here. And we see that the scale saturates as with ensemble member size of around 100. This indicates that maybe we should have more ensemble members. And maybe this conditional generative forecasting methodology can help us efficiently provide more ensemble members to exploit the seasonal forecasting capability of the underlying dynamical model. And finally, as I mentioned before, we can explore different ensemble strategies, model ensemble strategies. Here I'm showing the entity embedding vector. This is the T-SNE map, showing the distance between 2 points represents how closely they are in this model embedding space. And we see that these 2 different generations of CMF models, they largely form 2 groups, while the reality lies here. The reality is found by searching the optimal entity embedding vector using the observational data. And here is the result for temperature. We see that all the models, they roughly reside near this reality embedded vector, while for precipitation this is not the case. So we provide this conditional generative forecasting methodology which can learn from large climate simulation data that are generated by different climate models. And it can be taken as a bridge between traditional empirical forecast and dynamical forecast. And we can compare this methodology with the traditional dynamical forecast. It has several deficiencies and advantages. For the advantages, we are using the continuous simulation of climate simulations, so we avoid initialization shock by learning from an interrupted round of these GCMs. And we combine the power of multi-GCMs by learning from multi-GCM ensemble simulations. And we can make efficient sampling of forecast spread using a generative modeling framework. But there are also some deficiencies here. And we exacerbate initialization uncertainty by neglecting processes rather than the considered prediction source X. And we inherit some original GCM bias while introduce extra bias in building this statistical model. And finally, it's difficult to approximate high-dimensional distribution. As we might notice that some of the results here, although we are showing the scale here, if you look at the true prediction, it's much more blurrier than the dynamical forecast. And those are left for our future works. But I think it's a very good practice to disentangle the model formulation bias and the intrinsic climate variability noise, that the noise grown from uncontrollable initialization uncertainties. So we should separately treat these two different kinds of uncertainties to make utmost use of the data and to offer foresight about how we can make better signal forecasts. So that's what that's what I'm talking about today. And if you have any comments, please leave it beside this video. Thank you.